Okay. The rise of astronomy. And by astronomy, I don't mean just looking at the stars and drawing pretty pictures. By astronomy, I mean...
Do you put the things on PowerPoint online on camera?
Yes, I do.
Oh, because I was looking for them, I ain't seen them.
Yeah, they're in the modules on Canvas.
Okay.
But this one went up this morning.
Okay.
So you won't be able to, I haven't gotten them all done. I'm sort of barely ahead of where we are in the class.
Why
Okay.
would I go up on it to go to class material?
Yeah, if you just go straight to the home page is the modules, it's in the module for the chapter. Okay? So when I talk about rise of astronomy, I do not mean drawing pretty pictures by connecting the dots. Right? That's not astronomy. That's just drawing pretty pictures by connecting the dots. We all did that when we were, what, 4? Right? Those connected dot books, those were great when we were 4. But by the rise of astronomy, I mean actually looking at and understanding the world and what's going on. So, a big part is, fine. Why am I not full screen? There we go. All right. So, Aristotle was the first to say, you know what, I think the Earth's round. You want to know why he said he thought the Earth was round? He said he thought the Earth was round because the shadow of the Earth on the moon is round. Right? When you see a good partial eclipse of the moon, you get to see as it goes by and it goes through the shadow of the Earth, you can see that the shadow of the Earth is round. Right, now this is a bunch of pictures put together, but if you look at each one, here it looks like part of a circle, part of a circle. This is how it would look if it was going through a round shadow. And so Aristotle was the first to say, hey, it's round. This was, 300 BC or so. The other place where people began to think, hey, the Earth, she might be around, right? You like the oh, you guys didn't watch Bugs Bunny. You did? Okay. The Earth, she around? No, she a flat. No, she around, right? So, the Earth being round, another thing that people thinking that the Earth was round is if you look at the stars, if you were to be industrious and be in the right place, you could walk from the equator to the pole, North Pole. As you got farther north, eventually there would be stars that would go, as you walk north, they'd go lower and lower on the horizon, and eventually they'd be too low for you to see anymore. If the Earth was flat, that wouldn't change at all. The stars would always be at the same spot. Right? But because the Earth is round, as you go north, the stars go towards the south. Because you're walking around a ball. Right? Instead of just walking in a flat surface, you're walking around a ball. How far can you see? Here's a good question. How far away is the horizon?
10 miles?
It's closer than that. It's about 3 miles away. Right? If you're just standing up about 3 miles away, you can no longer see the surface. Now, you'll still see things, right? But at just a little bit more than 3 miles away, if you could see well enough, you would not see the tires on a car sitting on the road, because the road is curved over the horizon. And you still see things sticking up over the horizon, but the horizon is curving away, the Earth is curving away. Watching ships, for the Europeans, watching ships go out to sea and watching the ship disappear and then the mast disappear was one of the clues that, yeah, the Earth may be round, right? It's a difficult thing, if no one had ever told you the Earth was round, it'd be a difficult thing to kind of get on your own. There's another guy, we have any Greeks in here? No. All right, so I'm going to murder his name and nobody will know. Eratosthenes, 276 to 197, 195 BC. He made a trip from a place on the equator, the well Syene, and the thing he noticed there at this well was at noon the sun would shine straight down into the well. Right? Because it was on the equator, the sun, he got there when the sun was not at an angle, it shone straight down into the well. And so then he started paying attention and he went further north to Alexandria and he measured, okay, so at noon, what's the length of the shadow of the obelisk at Alexandria? Obelisk of Alexandria looks a lot like the Washington Monument, right? So he measured its shadow and he estimated, okay, if the sunlight's all coming straight in like this, so that it shines straight down into this well, and I can see the bottom of the well, and this, when I go further north, has a shadow, that means I've gone around a curve like this. And he worked out how big would that make the Earth. And he got 25,000 miles, which is within 25,000 miles in circumference, which was within 1,000 miles of the actual answer. And he did not have a calculator for doing the trigonometry. Right? He couldn't hit a button for pi. So this, little before, you know, little more than this would be at this point, 2,200 years ago, right? People were reasoning now, okay, the world's round and this is how big it is. About 75 years before that, another Greek. Now, I don't know how many other people in other cultures discovered things like this. Part of the reason we know about the Greeks that did this is because they did what? They wrote it down, right? So there's no telling how many other people discovered this, but it was never written down in a way that we could track or trace or know about, right? So, Aristarchus noticed how long it took the moon to go through the shadow of the earth, and he worked out, he was not as good a mathematician as Eratosthenes, but he worked out the relative size of the earth and the moon. He got kind of close on that. So the moon is about 0.27 size of the earth, and he got 0.35. And he also worked out how big the sun is by looking at, you know, if I look at the moon and I see it so that it is, half of it is illuminated, that means the moon is going straight towards the sun, right? And when it comes back over here and I see the same thing, the moon's pointing straight towards the sun, and I work out this triangle, I can figure out how far the sun is and how big the sun is. There, he was a little off. He got that the sun was 7 times larger than the earth. Well, you know, it's not off by more than a few hundred, so. And he got that it was a good bit bigger than the earth, right? Not nearly as big as it actually is, but he got that it was a good bit bigger. And so he tried to argue, you know, it makes no sense that we have the earth at the center of the universe, given that the sun is so much larger. The sun is probably the center of the universe. And that argument went nowhere for the next 1,600 years, right? Everybody still had the earth at the center of the universe. Another thing that we began to wonder about, and a technique that they used on some of the measuring things that are close to us that we still use today. We use something called parallax for measuring how far a star is. Right? So, for instance, if I wanted to measure the distance between you and me and get an estimate, right? And I'm the Earth going around the sun, I'd look at you and see who's sitting behind you at this time. And then 6 months later, I'd look at you and see who's sitting behind you back there. And I begin to work out, okay, I know how big this side of the triangle is, and I know now what the angle I've covered in looking at you is, so I can figure out how far away you are.
Is it like the Pythagorean theorem?
Yeah, Pythagorean theorem, trigonometry, you know, things we're not really going to talk about in here, but, right? But it's using the angles and using the sun at when the Earth is way over here versus way over there, and looking at that angle and saying, I can figure out how close, where something is that's closer to me than the background of stars. Now, some of these stars out here are really far away, right? I mean, some of them are not even stars. Some of them are galaxies. One of the galaxies we see all the time, Andromeda, is 3 million light years away. You know, our galaxy itself, if we could look all the way across it, is about 100,000 light years. So, you know, when we're looking at a star in our galaxy versus something that's so much further away, this actually works pretty well. And this is one of the techniques we still use today. Okay? We do careful observation of stars as they move against the background of the stars behind them. Now, it's not a big movement, but it's a little bit. And it's just enough for us to begin to measure distances. So, the other thing about the rise of astronomy is we began to realize that all the planets that we could see, the planets that they could see, the planets you can see with your naked eye, are Mars, Venus, Mercury, Mercury, Venus, Mars, Jupiter, and Saturn. Right? I saw something on Facebook the other day that said something about Mars being visible on such and such a date. The next time this happened was in several hundred years or something. I was like, okay, so there's a conjunction of Mars that happens, and it's not happening for a long time, but Mars is out there all the time. I mean, we see Mars a lot. You just don't know where to look for it yet, right? And we're going to work on where do you look for Mars in the sky. But all of the planets, we call them Galilean planets because all the visible planets, Galilean moons. All the visible planets orbit around the sun in the same plane. That means it's kind of like they're all on the same racetrack going around the sun, just at different distances, right? And that's also true of Neptune and Uranus, or Uranus and Neptune, but it is not true of Pluto. Every planet orbits the sun in a single, like it's a big flat pancake, except for Pluto, which is off on its own over here, you know, tilted at a different angle. So this plane, right, we call the plane defined by the equator of the Earth the celestial plane, or the celestial equator, because that's how we see the stars rotate, because we don't really see the stars rotate, it's really the Earth rotating, right? You know, I could stand here and get dizzy rotating around, and I could draw up a world in which you guys are the ones that are actually rotating around. It's just not true, right? So the stars aren't actually out there moving around the Earth. The Earth is spinning around, and because we're spinning around, we see them moving. Anybody that wants to come up here and spin around and watch everybody move, welcome to, but, you know, I think you all understand that piece, right? It's the Earth that's moving. And so we see everything circle us this way because that is the plane of our rotation. This plane that the Earth circles the sun in is called the ecliptic plane. Why do you think it's called the ecliptic plane?
The eclipse?
Because when we have an eclipse, it's because the moon intersects the ecliptic plane between us and the sun, or the moon intercepts the ecliptic plane behind us with the sun on the other side, right? That's when we have eclipses, is when the moon enters the ecliptic plane. That's the plane all the planets are in also. And in your book, you'll see, you can see a picture, I meant to grab it and forgot it, of what it looks like when there's an eclipse due to Mercury, which is the sun is still this big, bright ball and there's a little black dot on it. We don't call that an eclipse. Why? Because it doesn't cover the sun in any significant way. Right? You can't even see it, you can't see it with your naked eye. You can see it with your blind eye briefly. But you have to use special filters to make the sun dim enough to look and see where Mercury is as it goes across. Unfortunately, Mercury this year, this next year, this is so frustrating for me as a astronomy prop. Mercury this next year will cross across the sun again. Right? Doesn't happen often, and it's happening next year, and it's happening between summer sessions. Like, it's a rare event. Here it is. We could put the filters on. We could watch it, and there will be no students on it. All right. So we have the ecliptic plane where all the planets are. We have the celestial plane, which is how we see things rotate around us. The planets, just like with parallax, the planets appear to move in the sky for a couple reasons. One is they move, right? They are moving. The other, though, is we're moving relative to them. So if you look at this, here we are at in this drawing, the Earth is going around this way, and Mars is going around this way. So when we're here, we see Mars, right, against the stars over there. When we're here, we see Mars there. And so we see Mars go across the stars. If we had our planetarium, I could actually show you this, because I could speed up time in the planetarium, and you could watch the stars and the background of stars and the planets in front of them moving back and forth. All right. So it is this relative motion that generates what we see as the motion of the planets across the sky. Right? So the motion of the planets across the sky is a result of not only their motion, but our motion as well. So two pieces contribute to it. That's why we get some things that really used to confuse people, which is we get retrograde motion. Right? Now, in astronomy, you'll get confused when we have drawings in astronomy and we label it with directions. If this were a map, we'd say north, south, east, west, right? Because we draw maps when you're looking down at the ground. In astronomy, we're looking up at the sky. And so in astronomy, it's actually north, south, east, west. East and west are reversed because we're looking up instead of down. Does that make sense? Mm-hmm. If I'm facing north, I'm looking down at a map. East is over here, west is over there, there's north, there's south. If I'm now looking up, and again, when I've got it down here, I've got north at the top, south at the bottom, right? When I hold it up here, if I want north at the top, I have to turn around. Mm-hmm. Now I have north, south, east, west, right? So east and west are reversed. Now for you southern hemispheres, it's because we have this northern bias and we always want north at the top of the map. Right? But north, south, east, west. So when we're looking at the sky, east and west are reversed from what we're accustomed to. So here, this is Mars, right? At different dates. So Mars comes through, we see it moving, and then it heads back the other direction. And then it heads back this way. Well, Mars didn't change direction, right? Mars isn't going along in its orbit and then goes, I'm going to go this way a while. Then I'm going to go back this way, right? Mars is still going along in its orbit, but because the Earth is going around in its orbit, we see Mars move as we pass it. We see it move differently, right? And then it starts back the other way. We'll see that on a slide in just a minute, right here, right? So here we are, we're looking at Mars. The key is we move faster than Mars, right? We see Mars over here, then we get here, we see it there, we get here, and it started to move backwards. And it's going to continue to move backwards until we get past it. And once we're past it, it begins to move forward again. As we're passing it, it looks like it's moving backwards. It's like when you're in a car, passing another car, and you look over, as you're passing it, it looks like it's going backwards. Once you're past it, it looks more like it's following behind you, but going slower. Right? When it's ahead of you, it looks like it's ahead of you going the same way you are, but going slower. But as you pass it, it looks like it's going backwards. That's why we have retrograde motion in the sky. Because as we pass Mars, it looks like it's going backwards. We're just faster. Right? All right. Copernicus was the first to successfully sort of say, you know what? The sun should be the center of the universe. Right? Should be. Kepler began applying math to what he saw. Now Kepler had some really funny mathematics that he applied. But one of the things that remained, it's part of one of your problems, is that the relationship between how long it takes a planet to go around the sun and how far out it is this one, that the length of time it takes the planet to go around the sun in years, squared, everybody knows what squared is? Right? Is the distance to the planet in AU cubed. Right? Those two equal each other. This is a relationship that Kepler managed to map out, that if you square the number of years a planet is going around the sun, you get the cube of the distance from the sun in AU. Now, why does this work out if you use years and here and AU there? What is AU again? It's an astronomical unit, and it is the distance of the Earth from the sun. And a year is the time it takes the Earth to go around the sun once. Right? So there's a built-in relationship between a year and an AU, which is why this equation works out without having to have funky numbers for converting units. Right? All right. So Mercury, for instance, is at 0.4 AU. Right? It's at 0.4 AU. That's how far away it is from the sun. So if we wanted to know where Mercury is, or how long a year on Mercury is, we take 0.4 cubed, which is 0.4 times 0.4 times 0.4, which is 0.16 times 0.4, which is, no, 16 times 2, 0.064, something like that? Maybe?
It's not.
What's that? 0.4 cubed? How close was I?
Oh, wait, never mind. You were alright. I'm gonna just be quiet.
Alright, 0.4 times. Oh. I use the same 0.4 every time. Alright, yeah. Alright, so 0.064, right? So that means that P squared, the number of years that it takes Pluto to go, not Pluto, Mercury to go around the sun, is this P squared is 0.064. So P, the number of years it takes it to go around, is the square root of that. All right, take the square root of this, and I get 0.25 years, and is how long a year is on Mercury. 0.25 years. All right, so a Mercury goes around the sun every 3 months. All right, every 3 months. There are planets out there around other stars that go around their star every few days. They are very close to their star. Right? The closer you get to the star, the faster you have to go around. All right? So, what about Neptune? All right. Neptune is 30 AU away. So that means A cubed is 30 cubed. Let's see. 900.
27,000.
What's that?
27,000.
27,000. Right? So how long does it take Neptune to go around? So P squared, number of years squared, 27,000. So that means P is the square root of that. Right? P is the square root of 27,000 is
729 million.
You're sure you should square root?
Wait,
Because I got 164.
Wait, I'm confused on what you're supposed to.
We want P squared is the square root,
Out of the square root. Okay.
right? So I get 164 years. Right? So Neptune is way out there. Right? Neptune is way out there going slowly around the sun. Right?
That's how you figure out how long it takes for planets to go.
That's how you figure out how long it takes for planets to go around the sun. Once you know how far a planet is from the sun, you know how long it takes. Or once you know how long it takes for a planet to go around the sun, you know where it is.
So how long it takes us to go around the sun?
1 year.
Jesus.
Right?
Jamie.
1 year.
Oh, I wasn't listening when you said that.
What's that?
You don't have to listen to that.
Takes us 1 year. All right. Galileo really began putting it all together. He almost died for it. Would have if he'd stuck to his guns. But in the end, he said, all right, if you're going to kill me, I'll say, sorry, I didn't mean it. You know. But Galileo had something nobody else had. Galileo had a telescope. Right? So Galileo could see things others hadn't seen. So you know how the moon, Galileo was the first to, well, Copernicus said, I believe that the sun should be at the center of the universe. Galileo said, here's the evidence that the sun is in fact at the center of the universe. Now, the sun's not at the center of the universe, but it's at the center of the solar system, right? What Galileo could see with his telescope that was different from anything anybody else did was just like the moon has phases, right? Just like the moon has phases because it goes around the earth, Venus has phases. And the phases Venus has depend on whether or not it's going around the earth or whether it's going around the sun. Because everybody thought everything went around the earth. Right? Human nature, everything revolves around us. Right? So the phases of Venus proved that Venus was in fact going around the sun, not around the earth. Mercury has phases. Mars has phases. So Galileo, Jupiter has phases. Venus has phases. Galileo could see the phases of all the planets. The other big thing he had is Galileo could see 4 of the moons of Jupiter. And he could see that they went around Jupiter, which was the first time anybody had ever seen anything going around another planet other than the moon going around ours. So now Galileo had, okay, there are moons going around Jupiter, there's a moon going around us. And when I look at all the planets, because of the phases of the sunlight shining on them, because of the way the sun shines on them, right, they must be going around the sun. And he was the first to really put it all together. And then Newton, in his big work, Newton's work was called Philosophiae Naturalis Principia Mathematica. He wrote in Latin. I don't know why. Everybody did back then. It was serious, you had to write in Latin. Newton wrote his big treatise on classical mechanics, and he invented calculus along the way. Right? So he invented calculus. He wrote, this is how physics works, this explains the planets, this explains everything we know right now. He was slightly wrong about some things, and there was a French woman that fixed a lot of his problems that nobody knew about, because she's one of my favorite, her name is Amélie Marquis de Châtelet, and she's one of my favorite physicists because she had how much formal education? 0. 0, because women weren't allowed to go to university. And so what did she do? She hung out in the hall. And she listened to lectures hanging out in the hall. And she learned the math and the physics. And she took Newton's Principia and she translated it from Latin into French and saw that there were errors in it and fixed them, and then wrote some appendices for some new stuff that she worked on. And then she put it in her dresser drawer and forgot about it. Because it was her hobby, being the best physicist in the world. All right? 9 years after she died, they finally opened the drawer and they're like, what's this? So Newton added the math to it all. Kepler's math was really goofy, and he had things squiggling around and doing all kinds of weird stuff. Newton kind of explained everything we were actually seeing and brought it all together. Today, we're still using what Newton did. Right? We still use it building houses, we still use it in launching rockets, we still use it in calculating where the planets are going to be. We're still using all of that. Okay? Questions? Thoughts? Concerns? Needs, wants, ideas? We're not about to end, we're about to make a transition. Right? We want to talk more about how some of these problems go and how the quizzes go. Okay? Because we got half an hour. And I wanted this to be short so we could start talking about how to work problems. Unless you guys don't want to know how to work problems. Okay. All right. So, while we're about to get the irritating part of being on a computer you normally don't use, I'm going to launch Word. Find it. And it is going to take forever to launch because I've never opened it on this computer. All right, chapter 1 problems. It finally occurred to me, because a lot of you are probably wondering, why do we do things like figure out how to map the solar system to the clock, right? What's the point in that? What does it do for us to map the solar system to the quad?
Yeah.
What's that? It puts it in a size you can understand. Yep. Puts it into a size you can understand. The mathematics you use, however, is also exactly the math you use to convert a recipe from feeding 6 people to feeding 10. Right? It's the exact same mathematical skill. You're taking proportions and you're scaling them differently. Right? And so, while this is a science class, and yeah, it's great because it brings it into a, you know, if that's Neptune, then the first 4 planets are all right here. Right? They're all really close, and Jupiter's here, and then there's Saturn, and then there's Uranus, and sorry, and then there's Neptune, right? And it gives us that perspective of, you know, all the planets we see are relatively close together, and then there's a whole lot of empty space out there. Right? But the great thing about it is that math, that ability to change scales, is exactly the same math you need to convert a recipe. Now, if you're lazy like me, you go to all recipes and you can just put it in and it'll scale it for you. But it's the same math you need to scale that up. You know, it's the same math you need to say, I'm doing a party for 5 versus I'm doing a party for 50. Right? It's taking things and scaling them appropriately. What were the other problems we had?
Fish.
Milky Way the size of a nickel.
Milky Way, what?
The size of a nickel, 2 centimeters.
The Milky Way were 2 centimeters. You might remember which one that I
The
had.
cosmic landscape ones, right? It's not chapter 1.
Oh,
Yeah,
let me get it right.
Yeah, I did that too a bunch. It's on page 12.
All right. How big would the local group be? Okay. So how big is the Milky Way? right? Milky Way's, well, diameter is 100,000, radius is 50,000, right? So Milky Way diameter is 100,000. Let me do. Okay, so the diameter of the Milky Way is 100,000 light years. I write light years as LY. I think your book always spells it out, light years, right? So don't let my notation confuse you. And they want to say we're going to call that 100,000 light years 2 centimeters, right? We're going to say our scale factor is 2 centimeters. Now, if you've ever used a real map, how many people have ever used a real map? Right? Somewhere on it, there's a little scale that says 1 mile equals so much. Right? That's all we've done here. We've got our map of the local group, and we're saying 100,000 light years is 2 centimeters on our map. So if 100,000 light years is 2 centimeters, how big is the local group? How big is the local group? I might know it off the top of my head. I think it's 3 million light years. Maybe 5.
2.5.
Okay. So we'll go with 3. Right? This is astronomy. We're often very imprecise because when we're talking about 3 million light years, 2.5 doesn't really make any difference. Right? And we're like, hey, away, right? All right, so 3 million light years. So how many centimeters would 3 million light years be? If 100,000 is 2 centimeters, right? How much bigger is 3 million than 100,000?
60 centimeters.
Right, so this is 30 times bigger than that, right? That means this needs to be 30 times bigger. So this needs to be 30 times 2 centimeters, or 60 centimeters. So in other words, on our local group, if we drew the Milky Way this big, right? The local group would still be about that big, right? 2 centimeters, 60 centimeters, right? So our local group is about that big relative to our galaxy. And we are an itty bitty 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 dot in our galaxy. Does that make sense? So again, this is just scale factors, right? We define the scale factor. What was the scale factor I defined for you in the quad problem?
250.
I defined that 30 AU, right? We also said the solar system is going to be the size of the quad, right? So the scale factor I defined was 30 AU equals 250 meters. Pleasure. All right, other questions?
On the Milky Way, how you have it's 100,000 light years. This is its 50,000 light
Does it say its radius?
That's his rating.
That's its radius,
years.
right? So diameter is
Yeah, I got you.
twice that,
Yeah.
right? It's like in the movie Men in Black, little galaxy inside a little pin.
So on this next one, we're just using like an example. It's not like referring to any planet in particular, is it?
So, no, so,
Okay.
well, it is in the sense that Neptune is 30
Yeah.
AU away from the sun,
Yeah.
right? Neptune is the farthest out. That defines the distance between the sun and the farthest planet.
Okay, so is that what we're referring to, Neptune?
Neptune, yep. Neptune is 30 AU out. Other questions? So on the quizzes, are all of you doing the quiz with your book open and Googling and, okay. Okay, that's good.
Okay.
What's that?
Said I am now.
Yeah. All right, the quiz is for you to engage the material, right? So that when I start talking about it, you've at least kind of thought about it, right?
On the next, you asked your questions.
Do I ask your
Yeah,
question?
like the first question, chapter 1 homework.
First question in chapter one homework was what?
Getting it right. Yeah, the sky is not there.
Is that the one with if the earth turns one full?
Yeah, so you're getting the degrees of rotation per hour. But
Right.
then you asked how much does the sky turn or something like that, right?
Well, it's the same thing.
This is, but the sky doesn't turn.
Well, yes, the sky doesn't turn, but it's apparent motion because of our rotation